Let's test a Chapter 5 argument for validity using a truth tree. Here's our little argument. Not everything is G, therefore something is non-G. We set up truth trees just like we did in previous chapters. You put all the premises on the left of the line, put the conclusion on the right. We're picturing a validity counterexample. And then, just like in previous chapters, we want to break down non-branchers before we break down branchers. In terms of priority, we want to first do sentence logic non-branchers, that is, true and false negations, true conjunctions, false disjunctions. After that, we'll do quantifier rules. Note, all our quantifier truth tree rules are non-branchers. In terms of priority, we're going to do quantifier check rules first, and then star rules afterwards. So, sentence logic non-branchers, then quantifier check rules, then quantifier star rules. More about check and star rules in a moment, but let's see if we have any sentence logic non-branchers. And of course we do. That premise is a true negation. So we're going to apply the true negation rule. If tilde whatever is true, then whatever is false. That leaves us with false universal x, gx. Now we have two molecules to break down, false existential, false universal. False existential is going to follow a star rule. False universal is going to follow a check rule. So we're going to do checks before stars. We're going to do that false universal. False universal rule says if the universal sentence is false, then an instance of that sentence is also false. But there's this restriction. The instance we build out of this universal has to use a new name letter. And by new, we mean not appearing previously in this tree. Now, so far in this tree, there are no name letters, so we're free to use whatever name we want. So we'll build a little instance using A. If universal x, gx is false, then it's got a false instance, say GA. And we check that universal. We're only promised one false instance. We don't get to go back to that universal sentence for more instances, and that's why we check it. That leaves just the false existential. False existential is going to follow a star rule. Here's the false existential rule. If the existential is false, then you can build any old instance you want of that false existential sentence. In fact, you can build as many instances as you want. That's what the star means. After you've built one instance, you're not done with that. If that existential is false, if it's false that even one thing is tilde G, then it's false that A is tilde G. It's false that B is tilde G. It's false that C is tilde G, and so on. You can draw as many instances as you want out of that false existential. The star means you can go back for more if you want more. We're only going to need one instance in this tree, but that's the idea behind a star rule. You can reuse that sentence more than once. There's no restriction on the name letter we can use here, like there was with false universal. So we could build false tilde GA, false tilde GB, but what we want to do in order to keep the star rules from just going out of control is only build instances using name letters that you already find in the tree. Now in this tree, we have one name letter so far. That's A. So we're going to build just one instance of that false existential using A. So if existential x tilde gx is false, then in particular tilde ga is false. And you put a little star by that false existential, meaning you could go back and get more instances if you want more instances. Now we have one molecule left to break down. that is false tilde GA. That's a false negation. So of course it's going to use the false negation rule. If tilde whatever is false, then whatever is true. So since tilde GA is false, that means GA is true. Notice we've broken down all the molecules. This is the end of the line. Just as before, follow the path up from bottom to top like a bubble, and you look only at the atoms. In chapters 2 and 3, the atoms were sentence letters. We now have a new kind of atom, a predicate atom, like GA. Follow the path from bottom to top like a bubble, looking only at the atoms, and we see GA is on the left, and GA is also on the right. GA is true and false on this path, which violates bivalence. And that means that path closes. Since every path in this tree closed, all one of them, that means that this argument is valid. Well, of course it is. It's a little quantifier negation argument, but here's how you do a truth tree for an argument using quantifiers.